Hello and welcome back. This time we're looking into the graph of a rational function of the form linear over quadratic. So we're going to get started with factoring the denominator so that we can find the restrictions. In our case, the denominator x squared minus 4 will factor into x plus 2, x minus 2. So we'll say that x plus 2 has to be different than 0 and x minus 2 has to be different than 0 as well, which tells us that the restrictions are at x equals 2 and negative 2. So we'll say that x is different than plus minus 2. So that will help us state the domain, which is any real number x, except for the restricted values of it. So we'll write x different than plus minus 2. And from here, we can state the vertical asymptotes. We know that vertical asymptotes are equations of the form x equals restrictions, and we have two of them. So we'll say x equals 2 and negative 2 are both vertical asymptotes of this function. Next, we will look into the horizontal asymptote. Remember that when determining the horizontal asymptotes of a rational function, we first find what the highest degree term in the whole function is. The highest degree term here is 2. The other x term has a power of 1. So the highest degree term being 2 suggests that we rewrite the function in the form g of x equals, so I'm going to write the denominator first, x squared minus 4. There is nothing we need to change here, but since the numerator doesn't have an x squared term, I will write one with coefficient 0 and then plus x. Now the horizontal asymptote will always be the ratio of the highest degree term. In our case is 0 over 1. So we're going to say that horizontal asymptote will be y equals 0. So we're going to put this down on the table so that we have all the information organized. Next, we are going to find the intercepts. So for x-intercepts, remember that we set y equal to 0, which means that 0 must equal x over x squared minus 4. And that tells us that x must be 0. You can solve this equation by either making both sides into fractions and then cross multiply, or you can just reason about it and think, okay, so for a division to be 0, the numerator must be 0, so x is 0. So what we're going to do is write down the x-intercept, which will be 0. Now, for the y-intercept, we make x equal to 0. And another thing that I want us to observe in here and emphasize is that when x-intercept is at 0, that's where y is 0 as well. So we end up with the y-intercept also equal to 0. And if you want to evaluate it, fine, that's the same thing. So, and that will confirm our thinking. So y-intercept is 0. Now, you probably noticed that we have some conflicting information in here. So we have the x-y-intercept equal to 0 and the horizontal asymptote equals 0. So there is nothing we have done wrong. What we are going to do later as we graph it, I'm going to explain why and how this happens. We're going to check for symmetry. So first I check for even symmetry, which means that I check and see is f of negative x equal to f of x? If yes, then we'll say that the function has even symmetry. So f of negative x in our case will be negative x over negative x in bracket squared minus 4. So that would be negative x over x squared minus 4. And this is different than f of x. So therefore, we're going to say that this function is or does not have even symmetry. So once we're done with even symmetry, we check for odd symmetry. Now for odd symmetry, we have to check and see if the opposite of f negative x equals f of x. So what we do in this case is we grab this equation, which is f of negative x, and we give it a sign negative. So we're going to have negative x over x squared minus 4. So these two negatives will make a positive. And then we'll have x in the numerator, x squared minus 4 in the denominator. And we'll see that this is exact same as f of x. So we're going to say that negative f of negative x equals f of x. And that tells us that the function has odd symmetry. So we'll put this on the table. We'll say that this function is odd. Now we are not going to rush for the range, not yet, because it's better to determine the range once we have found the end behaviors of the function as well. So for the end behaviors of the function, we are going to check the following. What happens to y values as x approaches positive and negative infinity? And what happens to y values as x approaches the vertical asymptotes from the left and the right? Now the vertical asymptotes in our case are 2, which means that we will have to find the vertical asymptotes as x approaches, the end behavior, as x approaches 2 from the right, x approaches 2 from the left, x approaches negative 2 from the right, and x approaches negative 2 from the left. So let's check and see what happens to the graph of this function with our findings in here. And I am going to start by graphing the vertical asymptotes, which are at 2 and negative 2. So here we are. And I will label each asymptote by their respective equations. So this would be the vertical asymptote named x equals negative 2. And this is the vertical asymptote x equals 2. We said that the function has a horizontal asymptote at y equals 0, which we will graph as well. Y equals 0 would be the horizontal axis, right? X-axis. So we'll say that this serves as a horizontal asymptote as well, and the equation of it is y equals 0. Next, we are going to plot the intercepts. And strangely, we see that the x-intercept is cutting the horizontal asymptote. Is this possible? As a matter of fact, it can be possible for a horizontal asymptote to be intersected by the graph. Recall that horizontal asymptotes are defined as y values that the function tends to approach as x approaches positive or negative infinity, which means that as x becomes very, very large, the y values will approach 0, and the same thing as x becomes very, very small, or very large negative, the y values will approach 0. So since the asymptotes are defined for x values approaching infinity, they still exist, right, as horizontal asymptotes. But there is no guarantee that they won't be intersected by the graph of a function, okay, in between the vertical asymptotes especially. The vertical asymptotes, on the other hand, will never be intersected because restrictions can never be, we can never fail restrictions. We can never cross restrictions. We can't cheat on them. So, in order to predict the shape of this graph, what we are going to do first is we're going to use our practical method of graphing. Remember that when we draw the asymptotes, our graph or Cartesian plane is divided into the following sections. So in our case, 2 vertical asymptotes and a horizontal asymptote. We'll have this section here, 2, 3, 4, 5, and 6. Now, when we determine the shape of the graph, we look into the domain of the function because remember that the vertical asymptotes will cut the domain into 3 intervals, 1, 2, and 3. And for specific x values, the function will have a certain behavior, which means that it will be for x bigger than 2, for example, the function can be either in this section or in this section down below, right? So what we do to predict where the graph is going to be, remember, the rational functions are just curves that follow their asymptotes. So whether the graph will be in the section above the horizontal or below the horizontal, what we do is give x a specific value. In this case, I will try x equals 3. And we'll say that when x equals 3, the value of y will be 3 divided by 3 squared minus 4. So that would be 3 over 5. So the graph then must pass through the point x equals 3, y equals 3 over 5. Now remember, this is 1 and 3 over 5 will be somewhere in here. So the fact that the graph has a point in here, it means that the graph will follow the horizontal asymptote and the vertical asymptote in this section of the graph. And this will be the shape of it. Next, we are going to check and see what happens as x approaches negative infinity. So for this, similarly, we are going to use a value of x at negative 3. So we're checking this part of the domain. I'm leaving the middle part for later because this is going to be the more interesting part. Now, another thing that we can use in here to graph the other side of the function is the symmetry of the function. Since the function has odd symmetry, it tells us that if one piece of the graph is in this section, then the other piece, think about it, will be down here, right? To fit the idea that this graph will have even odd symmetry. However, what I'm going to do is double check by substituting x equals negative 3. And we'll have here negative 3 divided by negative 3 squared minus 4, which is negative 3 over 5. So negative 3 over 5 will be right here. So this is negative 1, negative 3 over 5, somewhere here. And then we are going to just above 0.5. And we will think, okay, so if the graph is here, it has to follow the asymptote, so the curve must be going this way around. And now we are going to continue with the middle section here, so between negative 2 and positive 2. Because the graph has an x and a y intercept right at where the horizontal asymptote is, what we will do is we're going to pick a value between the intercept and the vertical asymptote. And then we're going to say, let's check and see what the values of y become here. So in other words, we're going to take x equals 1, evaluate the function at 1. And that tells us that the function will have a value of negative 1 over 3. So at 1, the function will have negative 1/3. So somewhere in here value. And at x equals negative 1, similar to this, we want to know what is happening as we get closer to the other vertical asymptote. So the y value will be negative 1 over negative 1 squared minus 4. So in this case, we'll have y equals negative 1 over negative 3, or 1/3. So at negative 1, we have 1 in here, obviously, so 1/3 will be somewhere here. So the graph of this function will pass through these 3 points, and it will have to follow the vertical asymptotes. The shape of the graph in this case will be this. And it will be oddly symmetrical. So this is a graph of the function x over x squared minus 4, I think that we're ready now to state the range. As you can see, the function can be or can have any value of y. So we'll say that the range of this function is y ER. Now, about the end behavior, let's read this together. As x approaches positive infinity, the y values are above 0, so we'll say 0 plus. As x approaches negative infinity, the y values are below 0, so 0 minus. As x approaches the vertical asymptote 2 from the right-hand side, the y values are going towards infinity. When x approaches 2 from the left-hand side, the y values are going towards negative infinity. Next asymptote is at x equals negative 2. When we approach negative 2 from the right-hand side, the values of y are going towards infinity. And when we approach negative 2 from the left-hand side, the values of y are going towards negative infinity. And this is how you would sketch the graph the practical way. Now, I want to show you another method, a more sophisticated way of describing the end behaviors. And that would be by studying the equation. So here we go again. I'm going to create a little bit of room in here. I'll rewrite the equation so I can focus the camera. And we have x over x squared minus 4. So we are studying the end behavior, which means that we want to check and see what happens to this function as, and when we say to this function, we mean to the y values of it, right? As x approaches positive and negative infinity. So in order to find out what happens when x approaches infinity or negative infinity, the first thing that we want to do is simplify the function. And when we say simplify the function, we mean that if you substituted x by infinity here, then you will end up with infinity over infinity of some other version of it, which is undefined. So we will not want to simplify the x value. So we want to have either a numerator or denominator as a constant number. So I would take out the greatest common factor of the numerator, and I would try to take out the same factor from the denominator so that I can cancel it out. Now, in this case, the numerator has only one term, x, and x is its own factor. So I can take out x from the denominator as well, and then the denominator, the other factor of the denominator is x minus 4 over x. So simplify, and now this will prevent us from getting infinity over infinity. And we'll say that a more simplified form of this function would be 1 over x minus 4 over x. So now we say, okay, so if we send x to infinity, then we'll have 1 over infinity minus 4 over infinity. So which is basically 1 over infinity. And if you divide it 1 by infinity, we get 0 plus. So we'll say that as x approaches infinity, the y values will approach 0 from above. And isn't this the same thing we got on the graph of this function? So as x approached infinity, the y values were above 0. We do something similar as x approaches negative infinity, so we simply substitute x by negative infinity, and we'll have 1 over negative infinity minus 4 over negative infinity. So this will end up being 1 over negative infinity minus some 0 minus, which won't affect the negative infinity, the value of the denominator, and that would be 0 minus. So that tells us that as x approaches negative infinity, the y values will approach 0 from below it. So as you can see here from the graph, when x approached negative infinity, the y values approached 0 but they were always below 0. I'm going to try to do one more vertical asymptote. The other one is done in the same fashion. Remember that we had an asymptote at x equals 2. We want to check the end behavior of the function around the asymptote. Remember that rational functions are made of pieces, so each piece will have its own ends. And we are going to study or find out what happens to the values of y as we approach the vertical asymptote at 2 from the right-hand side and then from the left-hand side of it. So this is how we do this. And this is more of a calculus concept, and you're going to do it more if you take calculus course. And now we're going to check and see what happens as x approaches to from the right and from the left-hand side of it. So we want to investigate the values of y. So remember, the equation of the function is y equals x over x squared minus 4. Now, when it comes to discussing the end behaviors around the vertical asymptote, what we want to do is factor the denominator. So we have y equals x, and not only the denominator, so in any rational function which may bring, for example, higher than degree 1 numerators, right? So you factor everything. And what we see in here is x plus 2, x minus 2. And once we do this, we substitute x by 2 plus or 2 minus. So we'll do 2 plus first. So 2 plus plus 2, 2 plus minus 2. So that equals 2 plus, which is a number slightly bigger than 2. 2 plus plus 2 will give a number slightly bigger than 4, multiplied by, and we have to be careful with this. This is the key calculation in here. So imagine here you have 2 plus or 2.0001, take away 2. So we're going to get a 0 plus. Now remember, if a number is multiplied by 0, it will be 0. So 4 times 0 plus will be 0, positive 0. And 2 divided by 0 plus will be infinity. So based on this, we can conclude that as x approaches 2 from the right-hand side of it, the values of y will approach infinity. And if you look at our graph in here that we graphed using the practical method, the values of y do approach infinity as x approaches 2 from the right-hand side. And last, we are going to look into x approaching 2 minus. The same idea applies. We need to factor first, and we'll have y equals 2 minus over 2 minus plus 2, 2 minus minus 2. Now 2 minus means that we have a number slightly smaller than 2. So it's still a positive number. I'm going to leave it as 2 minus for now. And remember that 2 minus plus 2 will be like 1.999 plus 2, right? So that's like 3.999 or slightly less than 4. Still a positive number. Now the next number here is 2 minus minus 2, which means it's 1.9999 minus 2. So the difference will be negative 0. So remember that here we have some number. It's a positive number, it's less than 2. And we have 4 minus, which is again a positive number, like it's 3.999, multiplied by negative 0.0000. You can go as far as you want, right? So that would be practically 0 minus. So we have a positive number divided by a 0 minus, or in other words, to get a better idea what's happening here, we have 1.99999 divided by negative 0.00001. So that will give negative infinity. So that tells us that as x approaches to from the left-hand side, the y values approach negative infinity. So let's take a look at the graph. So when we approach to from the left-hand side, the graph for those values of x is going all the way down. So the y values approach negative infinity. In the same way, you reason about x approaching negative 2 from the right and from the left-hand side of it to determine the end behavior, so to determine the values of y. So I hope that this made sense. I hope you found it useful, and I hope that you're liking how graphing rational functions. They seem very difficult at first, but they're quite interesting actually to graph because they come in all kinds of different shapes. And while we go over each and every step, we kind of understand them better, how the behaviors are connected to each other, and how rational functions are formed. So again, thanks again for choosing to learn from me, and let me know if you have any questions. Bye for now.